Imagine two operators working side by side in the same facility, tasked with producing the exact same cattle ration. They are drilling from the exact same raw materials and checking their weights on identical, highly calibrated digital scales. The hardware matches too. Both are driving identical industrial mixers, and both have their final mixing timers set for precisely 4 minutes. But there is a deviation in their workflow. Operator A follows a strictly prescribed loading sequence, adding ingredients in a very specific order. Operator B loads ingredients based entirely on whichever storage bin happens to be closest at the time. The spreadsheet shows the exact same kilograms of grain, roughage, and supplement going into each machine, but inside the drums, the ingredients are being exposed to two completely different physical processes. This chart highlights a common but inaccurate assumption: the idea that loading, mixing, and discharging happen in separate, neat stages. In reality, the mixing stage overlaps almost entirely with the loading stage. These massive steel drums do not sit idle while operators dump tons of grain into them. The heavy internal augers are actively churning from the moment the engine starts. The machine's constant rotation integrates loading directly into the mixing process. The specific order of entry determines the mechanical environment each ingredient encounters. We can see how this works by looking at the timeline of a standard 10-minute batch. The ingredient dropped in at minute 0 stays inside the operating machine for a full 10 minutes, but an ingredient added at minute 6 only experiences 4 minutes of exposure before discharge. That 6-minute gap creates a different physical reality. The first ingredient is dragged through the bottom of the mixer, absorbing intense friction, crushing weight, and continuous cutting action while the rest of the batch is slowly assembled on top of it. Time inside the drum acts as a multiplier. An ingredient's chronological entry point defines exactly what physical forces it will endure. This effect is most visible with long forage or roughage, which relies on its physical structure to function correctly in the animal's digestive system. If that roughage goes into the mixer first, it faces the full, unbuffered impact of the internal knives. The machine systematically shreds the long stems for the entire duration of the loading process. Entering late in the sequence allows the roughage to ride higher in the mix, preserving those long fibers. Entering early can pulverize the material, erasing the original chop length created in the field. The sequence of the load engineers the physical architecture of the final ration. Beyond physical destruction, we have to consider spatial distribution, which becomes difficult when handling potent microingredients and supplements. This illustrates a critical rule on the mill floor: inclusion is not distribution. Verifying that a small dose of mineral supplement hit the digital scale confirms its inclusion, but it says nothing about where those minerals ended up in the batch. If that tiny volume of supplement is dumped in at the very end of the load, it has very little time to circulate. It often remains an isolated, highly concentrated pocket of nutrients riding on top of the feed. Liquids face the exact same mechanical reality. Pouring the correct volume of water or molasses into the drum at the wrong time creates heavy, isolated clumps instead of an even coating. Precision weighing loses its value if the chronological sequence restricts the machine from physically distributing the material. The industrial mixer is an interconnected ecosystem. Every choice alters the environment for the next choice. Introduce a wet ingredient early, and it dictates how fine, dry powders will adhere later. Overfill the batch size, and the internal circulation pattern stalls. Let the internal knives wear down, and an early loading sequence that worked last month may suddenly fail to break up cunts today. A single deviation at minute 1 triggers a cascading physical reaction across every subsequent ingredient. Look at the layout of a busy feed yard. When an operator alters the loading order to save 30 seconds of driving between storage bunkers, they inject unpredictable variation into the final product. Standard operating procedures provide the engineered framework necessary to control these physical forces and ensure repeatability. We can formulate the perfect diet on paper and verify every gram on a digital scale. But if the sequence changes, the feed changes. Formula consistency requires process consistency.